if you want to think of what these couplings are, if we just divide by f squared just to, then you can think about dimensionally what they are. In order for them to sort of match up with what we got from the loops, is that they have some mu dependence that looks like this. You can think of it as parameterized by some coefficients a and b. If I want to match up with the 4 pi f squared that comes from the loops, then I have to sort of say that there's a 4 pi hiding inside the LIs. So I can do that. And then there's some coefficients here. There's some mu dependence. And the scales that are in the coefficients are the high scales, like lambda chi and higher, and rho, those types of things. So let me just call it lambda chi. And then there's some numbers here, a and b, which encode the high mass physics. Now, the point of thinking about power counting is that thinking about the fact that the loops in these coefficients are the same size actually tells you that these AIs and BIs should be order 1. And this actually goes under the rubric of something called naive dimensional analysis. So what naive dimensional analysis says is that this cutoff that we put between the low energy physics and the high energy physics is arbitrary, and we could change it. We could change it by a factor of 2. And what changing it does is it moves pieces back and forth. But if we could move pieces back and forth, then you wouldn't expect that the two things that you're talking about would be different in magnitude, because we're allowed to move pieces back and forth. So you expect that the size of contributions from the coefficients are about the same size as the loops. And that's what that's this naive dimensional analysis. So changing mu moves pieces back and forth. The sum is mu independent. But each individual thing is not. And because we're able to move things back and forth, we expect them to be the same order in magnitude. And that is this statement here, that the AIs and BIs, once I account for the 4 pi's, so I can actually, with this argument, I can figure out where there's 4 pi's hiding in the coefficients, because I can identify 4 pi's in loops. And then if they're supposed to be the same size, I can also identify 4 pi's in coefficients. So if you had figured this out, I don't know, 20 years ago, then you could have got a PhD thesis like Anish Manohar did, which was 25 pages long. Short PhD theses do exist. OK. So what do we do in practice? In practice, we have to pick a value of mu, just like when we were talking about gauge theory, we need to pick a value of mu. There we were picking things like mu equals mb. Here what people do is they typically pick mu's that are high. So maybe they would pick the rho mass, maybe they would pick lambda chi, or they'd pick just something in between, like a GeV. These are typical values that people use. So what that means is that you've put large logs, you've removed all large logs from your coefficients. And that's because you want dimensional analysis to hold for your coefficients, because you don't know them. So you would like to have some power counting estimate for them, then you'd like to go out and fit them to data, and you'd like the result that you get from fitting to the data to agree with your power counting estimate to be so that you're happy. It turns out that it does. So you are happy. And so to avoid large logs in the story, you put the large logs into the matrix elements. So that's different than our story in gauge theory, where we were thinking that we would resum all the large logarithms into coefficients, and then our matrix elements would also have no large logarithms. Here we're just saying, well, let's allow for large logs in the matrix elements. But the story is also different from gauge theory in another way, which is that there's not an infinite series here of large logarithms that you need to resum. And that's related to the fact that the kinetic term didn't get renormalized. There's no mu dependence in the coefficients of the kinetic term, so when the loop graphs aren't having like coefficient squared, depending on mu, that doesn't happen. We simply have one log in our loop graphs, one log from our counter term diagrams. They explicitly cancel. There's no higher order terms. The renormalization group here is completely trivial. If you integrate, you just get one log. So there's not really even a reason to talk about it. Okay, so there's certainly some differences in this theory than there are in gauge theory. And so typically the paradigm that you have is you can calculate matrix elements. You're going to fit the coefficients. You think of enough experiments such that you can get all the information about those coefficients, and then you can think of other experiments and make predictions. Now, as you go to higher orders in the theory, you get more coefficients because you keep having to go to higher orders and construct higher dimension operators. And so the paradigm of figuring out how to fit the coefficients gets harder and harder. And at some point, you effectively lose predictive power because you can't think of enough observables that can be measured in order to fit all your coefficients. But certainly at order p to the fourth, people can think of many more observables. And actually, people have worked out p to the sixth as well here. So two-loop chiral perturbation theory is kind of the state of the art. Yeah.
Well, so why a large log in this case is not screwing up the material?
Yeah, so you could. It doesn't screw it up because it only happens once. So there's no sense in which. So basically, what you could say is you can say I have this matrix element. It's got a large log and a coefficient. The coupling isn't. It's not like large log times the coupling is something that you could count as ordered 1 because that's not going to reappear in the higher order when you go to the higher order. So you still have a large log, and you are allowed to say that that large log is the most important piece of my matrix element. But it doesn't repeat itself in the higher orders. Because once you go to higher loops, you're actually getting something that's power suppressed, not loop suppressed. So the loops are giving power suppression, and that changes a lot of things.